So why not? So it's a pleasure to introduce Olivier Pantz. He'll speak about dehomogenization methods, singular lattices, and regularization.
Thank you very much. So yesterday we already had two talks about dehomogenization. So what I will talk about today is strongly related to the presentation of Perl and of Groen. But I will try to focus on two particular points, that is when we have singular lattices and how we do perform the regularization of the orientation field. It will be more clear later. Okay, so first I will give a brief motivation and try to explain what we want to achieve. So in all my talk, so it's about structural optimization, and I will focus only on a very simple case, that is compliance minimization, and mainly in the two-dimensional case. So for instance, here is a classical problem where you want to compute the optimal cantilever. So it will be, you want to build a structure between the wall on the left-hand side and the right-hand side where you applied a load. And there is many techniques to do this. So just to name a few. So one of them is the level set method. So you start with a shape with many holes, and then you run your method and you get something like this, for instance. Okay. Another popular method is the simp method. So it's a little bit, it gives results that are quite similar. So in the simp method, you allow some kind of intermediate densities, and so it's a parametric optimization. But what you observe in those two cases basically is that, the size of the final details you obtain at the end are more or less of the same order than the size of the structure. Maybe, well, it could be 1/10 of the size of the structure, but it's really, really difficult to obtain finer details using those methods. And if you are interested in, for instance, optimization for 3D printing, so this is a classical kind of shapes you can obtain using 3D printers. And as you can see, there is a lot of microstructures, and even if you want to solve the direct problem on this structure, well, from the numerical point of view, it's almost out of reach. And if you want to optimize a structure in order to obtain something like this at the end, well, it's also out of reach. So you have to do something else, and the natural tool to treat the direct problem or the optimization problem is obviously the homogenization method. So Geoffroy is a kind of specialist of this kind of method. So the idea in this case is to describe locally the shape by density. So here I have represented the density of the optimal composite shape. And locally, if you zoom in at one point, your structure will look something like this. So it's here it's periodic optimization, a periodic composite, and in which each cell is a square, and in which you have drilled the hole, a rectangular hole. Okay, so from the mathematical point of view, this is really, really nice, because this is, well, if you are using periodic composites, it's not exactly the optimal shape, but it's almost very, very close to the optimal. But from the engineer perspective, it's not very useful because this is an ideal shape in some sense, and you cannot build it. You have no way to build this shape. So the purpose of the dehomogenization is to go a little bit backward, meaning that we start, it is post-processing of the homogenization method. So we start with the optimal composite, and what we want to find is a sequence of shapes, changing shapes, that does converge towards the composite shape. And in fact, this is really the right way to look at some structural optimization problems, because if you try to find the optimal shape, there is no optimal changing shape. Okay, so the correct problem is not to find the optimal shape, but to find a sequence of shapes that does converge towards the optimal. So the kind of sequences that we obtain are like this. So here is one cantilever with very, very few details, and we have a parameters epsilon that is of the same order than the scales of the finest details of our shape. Oh, sorry. And then we can build a sequence that does converge when epsilon goes to 0 toward the optimal composite shape. Okay, so we obtain something like this at the end. And here we are under the resolution of the screen, so we don't see the details very well. Okay, so the question is how can we build such sequences? So I will try to talk about this now. Okay, so I will present this method. Okay, so just to recall, this is a post-treatment of the homogenization. So the purpose is to find a sequence of shapes omega epsilon that does converge towards the optimal composite shape. Here epsilon stands for the length scale of the finest details. And one advantage of this method is that the computational time is completely independent of epsilon. So in particular, you do not have to perform any other kinds of compute. You obtain all your sequence for all value of epsilon in one go. You do not have to perform new computation for each epsilon. Okay, so here is the main ID. So the main ID is based on the introduction of something that we call a grid map. So on the left-hand side here, we have our meshed optimization domain, and the grid map is a map from the domain D of optimization into R2. And here we do not see it very well, but this is the image of this optimization domain D by a given grid map. And on the right hand side we construct a Y periodic shape where Y is the unit cell, which is a square in this case. And then we are going to multiply the domain omega, which is a periodic domain, by epsilon. We are going to let epsilon goes to 0, and we are going to pull back the periodic domain epsilon omega using the grid map. And this is the kind of, this is the kind of things that we obtain. Okay, so we obtain here is on the left hand side it's epsilon omega, and here is the shape once it's pulled back. So the effect of the grid map is that it allows us to deform the initial periodic structure so that it is not the orientation of the cells is not necessarily parallel to the horizontal and vertical axes. Okay, so we can change the orientation locally using this grid map. And what we obtain, in fact, is that locally we obtain a periodic composite, and the periodicity cell is the gradient of phi minus 1 of the cubic cell of Y. All right. So the output of the homogenization method is the local orientation of the periodic cells, and also some other parameters that will describe the size of the hole, but we are not interested in the size of the holes here. We are only interested in the orientation. A stands for the rotation field of the periodicity cells, so it's local. At each point it's different of the domain D, so it's a rotation. And in order to align our cells using this grid map with the cells obtained by the optimization by the homogenization method, we have to find R and phi such that the gradient phi minus 1 is proportional to A1, A2, and we express this as saying that it should be equal to the exponential of R, A1, A2 of phi. So R here will stands for the dilatation of the cells. So the bigger R is, the bigger will be our cells, and the smaller it is, the smaller will be our cell in the domain D. And so once we have done this, it's really easy to construct our shape sequences that does converge towards the optimal composite. So it's omega epsilon. It depends on phi, and it's the element of x in the optimization domain D, such that phi of x belong to epsilon times omega, where omega is our Y periodic structure. So in the previous slides, omega was independent of x, but if you want to change slightly the kind of microstructure you are using depending on the position x, basically the size of the rectangular hole, you can choose this omega depending on x. And it's quite easy to prove that in this case this shape does indeed converge toward the composite shape that you want to obtain. Okay. But here we have a slight problem, because depending it's not granted that for any given rotation field, that you can find a phi that satisfies this equation. So there is a condition on the orientation of your field. So if you look a little bit at the previous equation, if phi 1 and phi 2 are the coordinates of phi, you should have that the gradient of phi 1 should be equal to exponential minus r times a1, and same thing should be true for phi 2. So you get that this is a gradient, and so the rotational of this guy should be equal to 0. Sorry, I forgot. This is 0. Yeah. We should have this. Okay. And this condition is equivalent to say that alpha, so alpha is the angle such that A is a rotation of angle alpha, is an harmonic function. So if alpha is an harmonic function, and that is equivalent to this, then you have that well, this condition is also equivalent to the fact that phi is a conformal map. So a necessary condition for phi to exist is that the Laplacian of alpha is equal to 0. Okay. So what we want to impose, so after the homogenization method, it's not clear that the Laplacian of alpha is equal to 0. There is no reason for this. So we want to impose this condition, Laplacian of alpha equal to 0. The problem is that alpha is defined up to pi. Okay, and this is because the cell defined by A1, A2s by this rotation field is exactly the same that the periodicity cells defined by minus A1 minus A2. This is because the periodicity cells that we have chosen are symmetric under central symmetry. So we have that alpha is defined up to k times pi, and so it will be very difficult to impose that the Laplacian of alpha is equal to 0, because depending on the representation of alpha you have chosen in each point of your mesh, the Laplacian of alpha, well, does not mean a lot of things. So our idea is to change a little bit the variables. Instead of optimizing with respect to alpha, we are choosing beta. Beta is 2 times alpha, so that beta is defined up to 2k pi, and we choose b to be equal to the rotation of angle beta. And this rotation of angle beta is independent of the value of beta, the representation of beta you have chosen, because it's defined up to 2k pi. And then we can express everything in terms of b instead of alpha, and in particular the conformity condition, which was that the Laplacian of alpha should be equal to 0, translate as, sorry, I forgot a lot of zeros here, as the divergence of the wedge product between w, which is the first component of b, wedge, the gradient of w is equal to 0. So I forgot equal to 0 here once again. Okay, and this is nice because once again here w is well defined. So what we are going what we have to do is after the homogenization process, we optimize starting with an initial guess given by the homogenization method. We pursue the optimization, but we impose one other condition during the optimization, that is that this is equal to 0 So that's impose this. So we impose this condition during the optimization process. And as we have a very good initial guess, in a few iterations it does converge, and it doesn't change too much the optimal composite shape. So we get a new composite shape that is not really, that is a little less optimal, but that does fulfill this harmonic condition. And then once it's done, we can compute the grid map, and we can obtain a sequence of shapes that does converge towards the optimal composite. Okay, so why is that? Because if the domain D is simply connected, and if our field W is regular enough, then this condition is not only necessary, but it's also a sufficient condition for an existence of the map file. So we are very happy, and in the case of the cantilever it's enough, but in certain cases, as shown by Pearl yesterday, it's not enough because this condition on W that is regular is not always fulfilled. In certain cases we have some small singularities of W, and we want to keep them because they are important for the optimality of the shape. So we have some work to do in order to be able to take into account the case where our field W does contain some singularities. Okay, so this is just due to the fact, this previous result, to the fact that in a simply connected domain, if you have a rotational field, then it is a gradient. Okay, so now it started to get a little bit more complex. So our main idea is instead of looking for a grid map going from the optimization domain D into R2, we are going to construct some kind of abstract manifold that I denoted also D, but in another way, rounded D, let's say. So phi will now be mapped from rounded D into R2. And what this manifold rounded D is, it's basically two sheets covering of D. On each element X of D, an orientation A is given, and we have introduced previously, sorry, it's here, an equivalence relation between, I will say that two rotations are equivalent if you can pass from one to another by a central symmetry. Okay, so for a given point X, you have two options, either X and A of X, or an X and minus A of X. All right, so the next thing is now we are looking for phi from this rounded D into R2, and our sequence of shapes will be defined in a similar way than previously, except that phi depends on X and also on A of X. So there's two options for an element of for a given X, there's two possible A of X or minus A of X. But it doesn't matter because as this omega is symmetric by central symmetry, if you change a of x into minus a of x, due to this condition we impose on phi, this will be equal to minus phi a of x a of x. And so if this belongs to epsilon omega, it is perfectly equivalent to this condition. What I say is simply here that if phi verifies this condition, phi x a of x belongs to epsilon times omega. This is equivalent of phi x minus a of x belongs to epsilon omega. Okay, so now our purpose is to try to compute, if possible, this function phi here. And we can apply exactly the same method than before. And once you work on your variety, your manifold, instead of on the initial domain, in fact, you can reconstruct those two kinds of singularities. And in fact, there is only two possible kinds of singularities. So here we call it a positive singularity, because if you look at the degree of W on the boundary of this circle is equal to +1, and on the boundary of this one it's -1. That is why we call it a negative singularity. Okay, so in the case of one singularity is okay, but if you have more than one singularity, then it doesn't work anymore. You have to do something else. So we have to study a little bit more what is the topology of the manifold D. So here I'm going to construct the manifold D in the case where we have only two singularities. So what we can do is just we are removing the singularities and we replace it with little holes like this. And as I said, the domain, the variety rounded D is obtained, can be defined as a two sheets cover of D. So I have one cover here, one cover here, and then we have to glue them together in order to reconstruct our manifold. So I'm not sure that you can see it very clearly, but here I cut the domain along two lines, so this line here and this line here, and then this part, the top here of the cut, should be glued to the lower part of the cut here, and vice versa. The lower part of the cut here should be glued to the upper part of the cut here, and the same thing is goes for the next hole, the second hole. And so if you have more than two holes, it's exactly the same thing. And you can see that when you perform 2 times n cuts, so here I have made, in order to divide my initial manifold in two simply connected domain, I had performed 4 cuts, so the red one, the blue one, the purple one, and the green one. So with 4 cuts I have 2 simply connected domains. So if I had performed only 3 cuts, that is 2 times n minus 1, I will have D will be still simply connected. And it's the maximum number of cuts you can perform in order to keep D simply connected. And doing so, you can compute the dimension of the kernel of the rotational operator by the image of the gradient operator, and it's exactly this number, so it's 2n minus 1. So now if you have a field that is irrotational, we are going to add some kind of singular functions to it. We will be able to write it as the gradient of a function plus those singular functions. And a priori, it seems that we need 2 times n minus 1 singular functions like this. So here's the results. There exists a family of singular functions, psi k, that could be chosen antisymmetric and harmonic from the domain, the manifold D, into R quotiented by Z, such that, oh, sorry, I forgot a gradient here, such that for any regular rotational antisymmetric field V on D, there exists an antisymmetric map phi 0 and coefficient C in R n minus 1, such that V is equal to the gradient of all these things. So it's the gradient of psi 0 plus the sum of these singular functions, what I call singular functions. So what can strike you is that I'm using only n minus 1 function and not 2n minus 1. And this is because I have a condition on V. V itself is antisymmetric. It's not any irrotational field. And so on all the holes of my domain, if D, if I compute the integral over the boundary of V dot ds, it's equal to 0. So this is, I get using this end condition, and so in fact I do not need 2n minus 1 singular function, but 2n minus 1 minus n, and then it's n minus 1. So next things, from the practical point of view, we have to construct those singular functions. So we construct, in fact, one singular function for each hole. So we are using a little bit more singular functions than needed. For instance, here I have a small singularity on my field on one of those triangles, and then I create a path from the triangle where the singularity lies to the boundary of the domain, and my singular function psi is equal to 0 everywhere in the gray area, except along this line where it's discontinuous. So on one side of the line it's equal to 1/2, and on the other other side of the line it's minus 1/2. So you have a jump equal to 1 along this path, but it's not a problem because the value of psi are in R quotiented by Z. And moreover, it's antisymmetric. And next, if you want it to be an harmonic function, so this is a little bit useful on the next stage, what you can do is just orthogonalize this with respect to the image of the gradient. So and that's all. Okay. So once we have those singular functions, we can construct a new sequence of shapes that is a little bit more complex than the previous one, that will converge toward our composite shape. So we have the same ingredient, the same term as before. So before we had this term and this term and then this one. We just add the singular function times the coefficient ck. And the point is that, well, if we would like, we have to add some brackets here, and this bracket stands for the floor of epsilon minus 1 times ck. So this is an integer. And phi and the value, the coefficient ck, are computed by solving this equation. And we know that if the Laplacian of alpha is equal to 0, that such phi and such ck does exist in order to fulfill this. So in order to compute phi and the coefficient ck, what we do is just that we compute, we minimize the difference between this and this to the square, and it's just a linear problem to solve. Okay, so next we have another problem, because well, with this kind of tricks we can reconstruct shapes that does include a lot of singularities, but from the practical point of view we do not want a lot of singularities. Usually the singularities will appear in part of the composite shape where, for instance, the density is equal to 1 or the density is equal to 0, and meaning that the orientation of the field is not really important. And so it could be nice to, and due to this it does not give us very, very nice sequence of shapes. So we want to limit the amount of number of singularities in our optimal shape. So to this end, we add to the cost function, in this case the compliance, another cost that is inspired by Ginzburg-Landau energy. So the integral over d of the gradient of w, so w is the orientation of my cell, minus the w rotated by an angle pi over 2, so this is this guy here. Product tensor with A, so A is a potential, plus, no, I forgot the square, plus the rotation, rotational of A to the square, sorry for the square missing here, plus epsilon minus 2, the norm of W to the square minus 1 to the square. So when you minimize this function, it has two purposes. The first one is to impose that the norm of W is indeed equal to 1. And the second one is to limit the number of singularities. So if you are looking at this, sorry. So if you are looking at this first term here, if there is no singularity, it is equal to 0. Why? Because if there is no singularity, so W can be written as cosinus of beta sinus of beta. The gradient of W is the W rotated by an angle pi over 2 product tensor with the gradient of beta. And then you can choose your potential A to be equal to the gradient of beta, and you obtain that the energy of Ginzburg-Landau is equal to 0. So it depends only on the fact, so if there is no singularity, it's 0, and does not depend on the value of W outside of the singularities, so it depends only on the number of the singularities and maybe also on the respective position of the singularities in the domain, and nothing else. So it's exactly what we want. Okay, so that's what I'm telling this. This penalization function depends only on the singularity and the position in the domain. And you can, in the literature, you can find that this functional does converge when epsilon goes to 0 toward a measure of the number of singularities. So this is the main term of this penalization term. So this is some pictures that have been shown by Per yesterday. So this method could be applied, for instance, for the optimization of an electric mast. So here we applied loads on this side and this side, and the electric mast rests on the floor. Here it's clamped on the floor, and after the regularization, here we obtain two singularities. So one is quite difficult to see, but there is one positive singularity, one negative singularity here, and one positive singularity here. So maybe I can show you. Okay. So I've been doing the computation here because I have to redo them again. So if you are looking at the norm of W, you obtain this kind of field. So it's almost equal to 1 everywhere, except around both singularities where W does vanish. And if we are looking now at the lattice structure that we obtained, here we have chosen constant value for the size of the holes inside our lattice. You can see the two singularities. This one here is a negative singularity, and one of the top, which is a positive singularity. If you change a little bit the weight of the Ginzburg-Landau penalization, you can obtain an electric mass with 4 singularities. So the two previous ones, one here, and 2 other at the corner of your electric mast. And once again, the kinds of lattices you obtain are represented by this here. So you can spot the singularities here, 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 and here. And if you take into account the density, more or less the singularities does disappear, because you will not see really them even if they does exist in the final shape, because the density is equal to 0 here where you have one singularity. The density is equal to 1 here where you have another one, and 1 here where you have another one. And it's just for the last singularity where the density is neither 1 nor 0, where you can see the effect of this singularity of the final design. And we have also applied this to the 3-dimensional case. So for instance, here it's the results. So this is not the result of an optimization process, it's just the result of the projection for a given field. So here we have a singularity in the middle of this cylinder, and we obtain this kinds of pattern. And we can also obtain such thing like this for other kinds of fields. And to finish, there is also other kinds of applications, and I know that what we are doing are used also for image processing. So for instance, they are applied in order to spot the singularities on fingerprints. So we have tried to apply our method to this case. So here you can see on fingerprints you have very, very nice singularities. Here you have a positive singularity, and here I think we have a negative one, and here another positive one. Okay, so we scan this fingerprint. We give this image as an input our projection program, and we try to minimize the gradient of our image scalar product with W plus our Ginzburg-Landau energy, and then we are able to, in a second step, reconstruct our initial image using just the knowledge of the singularities and very few parameters. So you can see that this is a clean version of this one, and moreover, in order to obtain this, you have very, very few parameters in order to define such a shape. So it's kind of way to compress fingerprints, and it also can be used as it is compressed, in fact, to check different kinds of fingerprints, because you have a nice description of these fingerprints in terms of the singularities, the type of singularities, where they are, and things like this. So it's really more easy to compare two fingerprints. One is compressed, we're using this method rather than using the initial image here. Okay, thank you very much for your attention.
So you mentioned you have to compute numerically those singular functions that you call psi k. Can't you give those analytically?
Sorry?
Can't you give analytical formulas for those?
Can you?
Can you not give analytical explicit formulas for those? Why
No. Well, if you find one, tell me. I've tried, but the point is that, for instance, usually for this kind of fingerprint application, I think that it's linked to the fact that I have to define my singular function on the whole manifold around D. Okay. If you want it to define it only locally around one singularity, that's okay. You can find an analytic expression. But if you want something that is global, I don't think that you can get an analytical expression.
So here the manifold would be R2 in this example?
No. The manifold is not R2. Okay, the manifold is construct. It's a two-sheet cover of this domain. Okay, where your image is defined. And
but the singular function.
The singular function are defined. Okay, it's not
defined on a.
Sorry.
The singular function is defined on not on that manifold, but on one manifold with just one singularity, right?
I don't know if I. Okay, let me go back to.
Then maybe I didn't understand.
Yeah, I was not clear. Okay, let me see. Where is it? Okay. So my manifold is defined in the following way, and my singular functions are defined on the manifold. So I start with the domain D. I remove the singularities. So here and here I have two singularities. Once it's done, I perform a cut here, a cut here. I obtain two copies of D, and those two copies, in fact, on this domain D, I have a unit vector that is defined up to a sign. Okay? So I affect to one copy of D a vector with a given sign, and on the other another copy with the other sign. Okay, so that's I choose an orientation locally, and this is why I obtain two sheets cover. And then the varieties that I does obtain can be defined by gluing those two copies together, where you glue this lower part of the cut with the upper part of this cut, and so on. Okay, and it is on this variety that I do define all my functions. It is because I want basically the gradient of psi to be aligned with my vector W. Okay, but as initially W is defined just up to a sign, it has no sense working in the initial domain D. But when I have assigned a sign to W, what is done in the manifold D, then okay, I can try to find a psi such that the gradient of psi is equal to W. It has a sense. Okay?
Yeah, that's right.
No?
Maybe I can ask you later.
Okay.
So I was wondering about the following. So you start from kind of the periodic unit cell, which is characterized by some finite number of parameters L1 and L2, and then you rotate it.
Yes.
What if you were not just rotate it, but also impose a shear on it?
Yeah, yeah.
Of course, will have an effect.
Yes,
on the
of course.
homogenized matrix.
Of course.
And then you optimize over all possible shears under one linear constraint, that the shear, that the strain matrix field comes from a single displacement. And
yes.
so that to me looks at first glance a bit simpler than Is there a reason for not doing this?
Well, the main reason is that we didn't want to in fact, initially we tried to there's one lazy reason. So the lazy reason is that we do not want to compute the homogenized coefficient for too many variables. So if you allow shear or anything, other kinds of periodic cells, you have to also compute the homogenization coefficients for this case. And also initially we wanted to allow any kind of shapes, that is rectangular periodic cells or cells like this with shear. But in both cases, if you are looking at so when it's just square cell, in order to have a grid map, an existence condition for the grid map, it's simply that the angle alpha is harmonic. The Laplacian of alpha is equal to this, so it's very simple. And in this case, it translates in a condition that is more complex to handle. It's not linear. Okay, and it's more complex. And well, maybe we will do it later to see if we can impose this. It cannot be chosen arbitrarily. You have still something to.
Oh, yeah, but I didn't. Yeah, you're right. It's non-linear. I was thinking of the linearized Saint-Venant.
No, it's not linear. It's so here I think for this case I think it's achievable. You can do something, but in this general case it started to get quite messy. So I'm less confident.
You make some remarks on the complexity one would face in 3D with this D manifold.
Well, we have already performed. In fact, we are already using this D manifold in the three-dimensional case in the computation shown by Per yesterday. But we do not treat the singularities yet. Because it is a little bit more complex due, well, first from the computational cost due to the computation of the Ginzburg-Landau energy, and also it is a little bit more complex to construct the singular functions, but in theory it is exactly the same, and from the numerical point of view it will be also quite manageable, I think.
Yes, that's the second question. So I mean, from at some point in some talk there were pictures of a banana plant, and
a banana,
and also in Europe. I mean, when looking at fingerprints, of course you also do different. You see different types of singularities, which are more like dislocation lines.
Yes, that's true.
And so is it? I mean, so in a certain sense, your reconstruction rules out this type. I mean, you only look at these topological.
Yes.
Is there a way of kind of reconstructing those?
Yes. I don't. I don't know. I've thought a little about it, but I didn't find any nice solution. In fact, even if you have some kind of dislocation, you can see this like you can obtain it using putting a singularity and choosing wisely the value of epsilon, that is the distance between the ridges. But it's not natural at all. It's a little bit awkward to do this. And no, I didn't find any nice answer to this question yet.
Yes, so maybe I have a hint in this direction. So I think dislocation is a dipole of two singularities.
Yes, exactly.
Opposite sign close to each other.
Yes, that's it. Yeah.
So in principle, you can produce it using this method.
Yes, you can produce it, but depending on the value of epsilon you are choosing in order to reconstruct your image of the fingerprint, you will not obtain one dislocation, but you can obtain many dislocations, 2, 3, 4, depending on the value of epsilon you are choosing. So I'm not sure it's a very good idea to do this.
Further questions? Okay, let's thank Olivier again.
Thank you.